little bit of both. It's both a particle and a wave. And today we're really going to be looking at the wave-like nature of light. How does light operate as a wave? Well, you know a few things about waves. Like, for example, you know that all waves begin when the source of a wave is vibrating or oscillating. And it's the same way with electromagnetic waves. All electromagnetic waves, or light waves, begin when you have a electron that is, wait, let me change this. When you have an electron that is vibrating or oscillating. And so here's what happens is that you get a little electron, you get a little electron here that is vibrating or oscillating in place. It's going up and down and up and down like this. And when it goes up and down and up and down and up and down and up and down, that little electron is going to create a little electric wave. So you're going to get a little electricity wave here that goes like this from that little electron bouncing up and down. Now, we haven't really talked about electricity or magnetism yet. We talked very, very briefly yesterday about how an electromagnetic wave, a light wave, is a combination of electricity and magnetism, but really we haven't thoroughly talked about them. But here's all that you need to know for today is that when a little electron vibrates up and down, it creates a little electric wave. That wave, in turn, then creates a magnetic wave because electricity and magnetism are super, super related. They're super intricately tied together deep down. So when this electric wave is moving like this, it creates another magnetic wave. Now I'll try to show you this here with my camera, if it'll load. Okay. You might not be able to see this very well, so I'll do my very best, but I know likeness issues exist. So you have this electric wave that's going up and down like this. When that electric wave goes up and down like this, it creates another magnetic wave that's moving perpendicular to that wave. So if this wave is moving up and down, this wave is moving in and out like this. So you get two waves that are moving together kind of like this, interlaced with each other. An electric wave that's going up and down, and then a magnetic wave that's going in and out and in and out and in and out. And so I'll kind of try to draw this for you. And you can take a look, but you might be able to draw a better drawing here. You have this electric wave that's going up and down, and then you also have this magnetic wave here that's going in and out and in and out and in and out. So you can imagine that you have this little magnetic wave going in and out of the page, and then you have this little electric wave here that's going up and down and up and down and up and down. Now let's be very clear here that as this little wave is going, you have two little waves, one's going in and out, one's going up and down. The actual wave propagation direction, in other words, the way that the wave is going, is the wave is going forward like, excuse me, so sorry. The wave is going forward like this. It's traveling forward in space, but it has these two components, one that's oscillating up and down and one that's oscillating side to side. That's what an electromagnetic wave is, and that's pretty much all you need to know for today. Again, we'll jump in way more when we get into electricity and magnetism. This is kind of like a funky way to start without talking about electricity and magnetism, but that's all you need to know for today. There are 3 fun facts that you need to know about electromagnetic waves. 3 facts you need to know. Here's the first fun fact about electromagnetic waves. All electromagnetic waves... Oh wait, I already forgot my first fun fact. We'll start with the second fun fact then. Oh, wait, no, I remember. Sorry. Okay, the first fun fact is that there are 2 types of waves in the world. There are transverse waves and longitudinal waves. The first fun fact is that all electromagnetic waves sorry, it's going to take us like 5 years to write this. All electromagnetic waves are transverse waves. That's our first fun fact. You can see that those electromagnetic waves, they have crests, they have troughs, and so all electromagnetic waves are transverse waves. That's our first fun fact. Our second fun fact that you need to know is that electromagnetic waves can travel in a vacuum. Now, when I talk about how electromagnetic waves can travel in a vacuum, you know that this is true because you can see the light from the sun. If you couldn't see the light from the sun, or if light couldn't travel through a vacuum, there'd be no way for the light from the sun to get to us. But you can see the light from the sun, and you can see the stars at night. So you know that electromagnetic waves have to be able to travel from that thing to us, which is through a vacuum. So we know that electromagnetic waves can travel in a vacuum. Now, when I say this is like point 2 of like a list of 3 fun facts, and it seems pretty insignificant, but this seriously like blew up the physics community. Like all the good people in the physics community freaked out about this because every wave has to have something to carry it. Like a sound wave is carried by little squishes of air molecules. A water wave is carried by the water. They say, how could energy be carried forward or move anywhere if there's nothing to carry it? And so for a long time we had all of these proposals about, well, maybe there's this stuff called the ether that exists everywhere, and it's just this ether that we can't see or detect, and it doesn't show up in any of our experiments. But maybe there's this stuff called the ether that's what carries light forward. But then Albert Einstein came along and said, what if there's nothing? What if light can just travel through a vacuum? And that's where we landed. We say that light is self-propagating, meaning it can carry itself through a vacuum. Because that electric field creates a magnetic field, and then the magnetic field creates an electric field, and then the electric field creates a magnetic field, it creates itself, it pushes its own self forward. And so electromagnetic waves can travel in a vacuum. They do not need a medium through which to travel. That's our second fun fact. Our third fun fact is that all electromagnetic waves travel at the same speed. And that speed is 299792458 meters per second. Except people got very tired of always saying 299792458 meters per second, and so we abbreviate it with the lowercase letter c. All electromagnetic waves can travel to speed c. And they all will in a vacuum, regardless of the frequency or of the amplitude of the wave. Now, we've covered a little bit about electromagnetic waves. You see what they look like. You see the 3 facts about them. We have 3 items on our agenda for today. The first item on the agenda is to talk about what an electromagnetic wave is. And we've done that. Huzzah! The second item on our agenda for today is to talk about polarization. Polarization. Yeah. And the third item on our agenda for today is to talk about the electromagnetic spectrum. We have accomplished the first task. We've talked about what an electromagnetic wave is. Then we've talked about 3 facts about electromagnetic waves. Now we're going to talk about polarization, and then finally we'll talk about the electromagnetic spectrum. Let's start by talking about polarization. I'll change up my color here so that you know it's a new topic. Let's talk a little bit about polarization. The first thing that you have to understand about polarization is that polarization has to do with the orientation of light waves. And let me show you here, polarization. I'll show you with my camera. And I need a little electron, so hang on, let me find it. Okay, yes, for today, for my little electron, we are going to use this Flower Street Farm Lavender Vanilla Lip Balm that is conveniently shaped like a little circle, and it will act as our little electron for today. I am not, to be very clear, sponsored by Flower Street Farm whatsoever, but they are local, and so you could buy Flower Street Farm Lavender Vanilla Lip Balm. This is available to you. Anyway, moving on. Here I have this little electron. Now, if this little electron vibrates up and down like this, it will create a little wave that goes out up and down like this. But if this little electron vibrates side to side like this, it will create a little electromagnetic wave that goes side to side like this. It could also vibrate at a diagonal, up and down like this. And that would create a little wave that goes off at a diagonal like this. Now, notice that all of these waves, like this one going up and down, creates a wave going this way. This one going side to side creates a wave going this way. Notice that they're all moving the same direction. The direction of the propagation is the same for all three, but the direction of the orientation of the wave depends on the direction of the orientation of the vibration of the electron. The light that comes from the lights in this room right now, or the light that comes from the sun, is made up of light from electrons that are all vibrating in all different directions. Some of them are going up and down, some of them are going side to side, some of them going at a nice diagonal. And so you get waves that are all oriented in all different directions. Some of them are up and down, some of them are side to side, some of them are at a nice diagonal. So you get all different orientations of light waves. This is what we call unpolarized light. Unpolarized light occurs when the light waves from the source are oriented in every different direction. That's the first thing that you have to know. If I were you, I'd take a moment here and I'd write that down somewhere, that all unpolarized light is light that has light rays that are oriented in all different kinds of directions. There's your first kind of vocab term. There's your first definition. We can do what we call polarized light. And polarizing light means we take that light that's oriented in all different kinds of directions. We got some going vertically, we got some snaking horizontally, we got some going at diagonals, and we filter it so that the only type of light that makes it through is all going in one direction. I'll kind of show you what this looks like. Doop-a-doop-a-doo. Oh wait, first, back to the camera. So sorry, team. Here, I have my polarizing lenses. These lenses, what they do is they polarize light. So they filter out light. Light is coming into these lenses going all different directions, but on the other side of the lens where my eyes are, the light is only going one direction. Allow me to show you how they work. Oh, not that, this. Okay, here's how these things work. You could imagine that my polarized lenses on my sunglasses are kind of like little gates. Now this is an analogy, this isn't totally true, but the idea of the analogy is that if you zoom in super, super far on my sunglasses, what you would see, oh gosh, wait, I don't want that there. What you would see is that my sunglasses look kind of like gates like this. Now you could imagine that if you had a horizontally polarized light wave. In other words, you have a light wave that is horizontally oriented. If that horizontally oriented light wave is coming at that gate like this, that horizontally oriented light wave, when it gets to the gate, it won't be able to make it through. But if you had a light ray that was vertically oriented, that was going like this, that light ray, when it gets to the gate, would just be able to slide right through those little cracks. And so a polarizing lens polarizes light so that everything that comes out on this side is vertically oriented, because the horizontal light waves on their way in, they can't make it through the gate, but the vertical ones, when they hit the gate, they can just slide on through. They don't just have to be vertically oriented though. You could have other types of lenses or other types of polarizing lenses. Imagine, for example, if your polarizing lenses looked more like this. Hey, go ahead and answer this question in your head and in your heart. What kind of light would make it through this lens, and what kind of light would not make it and would get blocked out? Did you say that horizontally oriented light would be able to make it through and that vertically oriented light would get blocked out? Because that's totally true. This kind of lens would let all the horizontal light through because the horizontal light could slide through the cracks, but it would keep out all of the vertical light. Here, let me show you this. Here I have two polarizing filters. I have this one right here and this one right here. Right now, when they have the little dots up, both of them are horizontal polarizers. Oh gosh, both of them are horizontal polarizers. So they're only letting light through horizontally. If I put them on top of each other, like this, you can see that you can still see through them pretty well because all the horizontal light is getting through. But watch what happens if I take this front one and I just turn it oh so slightly. Well, first, you know that if I turn it, here it's acting as a horizontal polarizer. It's only letting the horizontal light through. Here it's acting as a vertical polarizer. It's only letting the vertical light through. So when I take these and I put it on top of each other and I turn this, you can see that none light gets through. You can see the reflection of my computer screen. Whoa! You can see that none light gets through. Why? Because the front one isn't letting through any of the horizontal light, and the back one isn't letting through any of the vertical light. If I turn this back again, then you'll see that you can see my bookcase again. Check it out one more time. I'll try to get it so that there's not a lot of glare from the computer screen. Okay, check it out again. Ready? All the light gets filtered out, and light can make it through again. That's a little bit on polarization. Did you know that snow and horizontal surfaces are actually great polarizers of light? That's because snow and all horizontal surfaces polarize light horizontally. And there's a reason for this. If you've ever tried to skip a rock before, you know that if you take a little rock and you try to skip it across a pond, you can't choose just any rock. You mostly want a little flat rock. And if you take that little flat rock, you hold it in your hands like this, like your little flat rock oriented this way. You hold it in your hands like this, you flick your wrist, you let it go, and you watch it across the surface of the pond. What you would never do if you wanted to skip a rock is you would never take that little rock and whoop, turn it on its side up like this, grab it from the edge and chuck it in like that. You know that if you took a little rock and you went, then that little rock would go, and it would sink straight down towards the bottom. The same thing happens with light rays. If you take a light ray that's vertically oriented and you send it in towards the snow or towards the ground or towards the surface of the pavement on the roads, that light will hit that snow or the pavement and it'll just sink straight on in. But if you have horizontally oriented light that's moving like this, it'll hit the top of the surface and it'll bounce back off again just like a skipping rock. So most of the light that comes bouncing off the snow is horizontally polarized because the snow skips the light that is horizontally oriented, but the light that's vertically oriented sinks into the snow. This means that most of the glare that you're seeing that comes off of the snow on a really bright snowy day or off the streets when the streets are wet and you got a lot of sunlight reflecting off the streets, most of that light is horizontally oriented. If you wanted a pair of sunglasses that reduced glare, what kind of sunglasses would you want? Would you want sunglasses with polarized lenses that look like our first gate here, or sunglasses with polarized lenses that look like our second gate here? Did you say that you would want these ones? The ones that are vertically oriented? Me too. And it turns out that all of the sunglasses companies say the same thing. They say, hey, if we vertically polarize our lenses, then when the light waves that are horizontally polarized from the glare coming off the snow or coming off the streets, those horizontally polarized light rays will not be able to make it through our vertical light ray or our vertical polarization. And so what will happen is we'll reduce a ton of glare that's making it to your eye by having our lenses vertically oriented. And you can see that here if I take my sunglasses. Here they are. And I take one of my little polarizing filters here. You can see that if I hold up my, wait, let me show you the orientation here. You can see that if I hold up my polarizing filter like this, you can't see through the sunglasses at all. I got this one is horizontal. My sunglasses are vertical. If I turn it so that this one's vertical, you can see through my sunglasses again. Watch one more time. I'll turn this way. You see my sunglasses go completely dark. Turn it back this way, and you can see through my sunglasses again. That's because my sunglasses are vertically polarizing sunglasses. That's a little bit on polarization. We're now ready to address our third topic, which is the electromagnetic spectrum. Let's give ourselves a little check mark here. Yay! Success! Now we'll talk about the electromagnetic spectrum. And to do this, I'm going to grab a new drawing for us here. Please wait momentarily as we get this all pulled up and ready to go. Okay, yes. And now, here we go. This is topic number 3, the electromagnetic spectrum. And I'm going to draw a wave. Okay, it looks kind of like that. That's not like great, it's not superb, but that's okay, it'll do. When we talk about light in the electromagnetic spectrum, it turns out there's not just one type of light. And you know that that's true, that there's not just one type of light, because different things have different colors and different things look different. And so you know that there's not just one type of light. There are actually many types of light. And what determines the type of light that you have is the frequency of that light. It's how fast that little electron is bobbing up and down. Now over here, what I've drawn is a representative drawing of the electromagnetic spectrum. This is a representative drawing of all of the different frequencies of light, all the different frequencies that can be considered light, from the lowest frequencies over here to the highest frequencies over here. Over here, you see that we have really low frequencies and really large wavelengths. Over here, you see that we have really high frequencies and we have really small wavelengths. So we got low frequencies, large wavelengths over here, high frequencies, small wavelengths over here. Now, all of light can be classified as different types of light based on its frequencies, based on how fast that little electron is vibrating up and down. Now, here's one thing that you need to know is that last unit, when we talked about waves, we talked about how the energy of a wave corresponds to the amplitude of the wave. If the amplitude of the wave is greater, we have more energy. If the amplitude of the wave is smaller, we have less energy. Well, that's still true, but also there's another factor that impacts the energy of a wave. And that other factor is the frequency of a wave. If a light wave has or an electromagnetic wave has a much higher frequency, that's a higher energy wave. If a light wave has a lower frequency, that's a much lower energy wave. You can imagine this because if you had an electron that was just kind of like bouncing up and down very slowly, very casually, you would say, yeah, it doesn't look like it has a lot of energy, and that'd be a nice low frequency. But if you had an electron that was going crazy fast, you would say, whoa, that looks like a super high frequency electron. That looks like it's having a lot of fun, and it's taking a lot of energy to do that. So we see that our lower frequencies have less energy and our higher frequencies have more energy. Now on this spectrum of light, this is all of the different types of light based on their frequencies. You can see a very small portion of the spectrum. Not all of this light is visible light. I would say you would have about this much of the whole spectrum that is visible light. And we'll like blow that up. Here's like my zoomed in picture. We'll blow that up and break it down a little bit. It turns out that visible light, which is the light that you can see, is light that has a frequency range from about 4.0 times 10 to the 14th hertz up to about 7.9 times 10 to the 14th hertz. In that general kind of range. Visible light, in this little range right here, this little range, which is the range of light that we can see, makes up about 0.0035% of the whole electromagnetic spectrum. If you're saying, wait a second, Miss Wilson, are you saying right now that of all of the light that exists in the world, I can only see 0.0035% of it? Yes, that's what I'm saying. You can only see 0.0035% of light. All of the other frequencies of light are completely unavailable to you. This is all that you can actually see. Now, when we look at this light, we know that the frequency of the light, when we're talking about visible light, the frequency of the light determines the color of the light. For our low frequency light over here, our low frequency light is the color red. I'll make that a little bit bigger, is the color red. Our high frequency light over here is the color purple. And all of the other colors kind of line up between those. So right slightly below purple, the next frequency of light that you can see is blue, a little bit lower frequency than purple. The next lowest frequency light that you can see is green. Then the next lowest frequency that you can see is yellow, followed by orange. And lastly, the lowest frequency color of light that you can see is red. So you get a nice little Roy G. Biv action going on in here. Those are all of the colors that you can see. Now, there are also frequencies of light that you can't see. Slightly above visible light, slightly above purple, we have a frequency of light here, or a range of frequencies of light that we call ultraviolet light, or UV. UV or ultraviolet, where ultra here stands for above and violet stands for violet. Ultraviolet light is light that has frequencies just above that of violet. You can't see UV light, but you can certainly feel its effects. Ultraviolet light is a very high frequency, small wavelength kind of light, so it has it has a lot of energy. It's a very high energy form of electromagnetic waves. When this very high energy light interacts with your skin, it has so much energy that it can literally knock electrons off of the atoms that it comes in contact with. If it comes in contact with atoms in your skin, then it's knocking electrons off of the atoms that live in your skin cells, which can forever chemically alter what your skin cells look like, or what those little atoms look like in those little molecules. And if it happens to hit a molecule in a very important part of your skin, say like your, DNA, you could see how this would very quickly become very, very dangerous, and we would call it cancer. What happens is those little electrons get knocked off of your DNA, forever chemically alters your DNA. This mutation can turn into cancer. When your skin becomes tan in the summer, what your skin is doing is it's producing a lot of melanin. That melanin's job is to absorb the UV light before it gets to the deeper layers of skin where all of the important stuff lives. So if you see someone looking very tan in the summertime and you say, hey, nice tan, what you're saying is, hey, your body is doing a great job of trying to protect itself. Your security measure, your armor against the UV rays that are constantly bombarding your skin is looking very, very nice. Way to go, you. That's what you're really saying to someone, because that's what their body is really doing, is trying to protect from these UV rays. Now, UV rays aren't the most dangerous form of rays because there are certain frequencies of light that are higher up than UV rays. The next part of the electromagnetic spectrum is what we call X-rays. Now, students like to say, Miss Wilson, when you say X-rays, are you talking about like the type of light rays that you get when you go to the doctor and get an X-ray for your broken bone? Yes, that's exactly what I'm talking about. X-rays are even higher frequency than ultraviolet, and that's why they have so much energy. They can penetrate straight through your skin and through your muscles and through your tissue, straight all the way down to your bone. When they hit the bone is nice and dense, and so that's when they finally get reflected. X-rays, because they are so high energy, they are more dangerous than UV rays. You ever wonder why you go to the doctor's office and the doctor to get an X-ray, and the doctor says, hey, can you please wear this giant metal toga? And you say, yeah, sure. And then the doctor says, okay, now we're going to take a little X-ray. If you could please lay on this giant scary machine, underneath this giant scary machine thing here, and while you stay there, I'm just going to go leave the room, but don't worry, I'll be like right on the other side of this like really protective wall here. So I'm not gonna be here, but you have fun. I'll see you back in a second after your X-ray. And you say, wait a second, so you're just gonna abandon me here? Why do they leave the room? Well, because X-rays are dangerous. They're not safe. Now, are they great for getting a good picture of your bone one time? Sure, yeah, totally awesome. But like, do you want constant exposure in your life to X-rays? No, you really don't. That's why they do things like put that big metal toga on you. That's to help prevent those X-rays from getting to other parts of your body. So it's to help keep you safe. Next, After X-rays, we do have a frequency of light that is even higher up on the spectrum, and those are called gamma rays. Gamma rays are incredibly dangerous. They're incredibly high energy, and you get this kind of radiation a lot of times if you have like nuclear bombs and that kind of stuff. You also get other types of radiation then too, but when people are talking about like all of the dangerous radiation from nuclear bombs, what they're talking about is these gamma rays and other types of radiation. But a lot of what they're talking about is gamma rays that are just constantly bombarding people's cells. It's so high energy, it kind of acts like a little bullet just tearing straight through your cells and causing tons of damage, wreaking tons of havoc. So gamma rays are not great for you, should be avoided. We also have different frequencies of light below visible light. Like right below visible light, right below what you can see, we have a set of frequencies of light that we call infrared. Infrared light is not light that you can see, but it is light that you are familiar with. Because infra, meaning below, red, meaning red, infrared light is what you commonly know as heat. Infrared light is what you commonly know as heat. If you were to take a hot mug of coffee and you were to put your hand just to the side of that mug of coffee, you could feel heat radiating off of that coffee. The heat that's radiating, that radiating heat that you feel, that's infrared light. You're feeling infrared. If you feel the sun on your skin on a nice warm summer's day and you feel the heat from the sun, that heat is infrared light. It's light that's just below that of visible light. Now, infrared and red are super close together. You can see those frequencies are right next door neighbors on the electromagnetic spectrum. And so a lot of times if you're experiencing infrared, you're also experiencing a lot of red, which is why we associate the color red with heat. Because something that's giving off a lot of infrared is often also giving off some of the red frequencies as well, since they're right next door neighbors. Like if you've ever seen those outdoor heaters use infrared light. They shine infrared light down on you and you feel nice and warm. But if you look up at them, you'll see that they also glow with kind of a reddish color. That's because infrared and red are right next door neighbors on the electromagnetic spectrum. There are, of course, frequencies of light below infrared. Below infrared, in this region of frequencies, we get a region of frequencies that we call microwaves. Now, students like to ask, Miss Wilson, when you say microwaves, do you really mean like the microwaves, like what I put my food in to like cook it? Yes, that's exactly what I mean. A microwave is this wave that's just below frequencies of infrared light, and we use it to cook our food. The way that we use a microwave to cook our food is that you put your food into this microwave, and when you put your food in the microwave, close the door, start the oven, what it does is it sends microwaves literally into your food. Those microwaves, when they get into your food, they start to spin water. Because the water molecules are polar molecules. And polar molecules will respond to a little bit of electricity. They got a positive side and they got a negative side. Well, microwaves are electromagnetic waves, so they have a little bit of an electric element to them. So when those electromagnetic waves hit that water molecule, it spins the water molecule, causes the water molecule to spin. When the water molecule is spinning, all of a sudden now it has kinetic energy. And we know from back in Unit 7 on thermodynamics that if you got something that has some kinetic energy and you touch it, we call that heat. We say that it has some heat, it has some temperature, it has some thermal energy. So if you're touching something where the little water molecules are spinning, you'll feel it as hot. This is why a lot of times in microwaves, your food will be kind of patchy. There will be warm patches and cold patches. That's because the warm patches are places that did get zapped by microwaves. So those little water molecules are spinning crazy fast. But the cold patches didn't get quite hit with the microwaves. The microwaves missed that spot. And so those water molecules are sitting there relatively still. And so it doesn't feel as hot to the touch. This is why a lot of microwaves have those nice spinning trays down in the bottom to try to get all of your food covered by the microwaves so that all of those little water molecules start spinning. You've also probably noticed before that on your microwave, I keep looking over here because my microwave's over here. You've also probably noticed before that on your microwave on the front of the door, you know how there's like that metal door sort of situation with the little like holes poked in it? Do you know what that's for? Why we have that? Well, here's the thing is that people did not really feel very comfortable about putting their food in a giant metal box, pressing start and letting it run for 10 seconds, then taking it out of the metal box and eating it. That just felt uncomfortable to people. So something that people liked is they like to be able to look into the microwave and to see their food as it cooked. Now, if you want to look into the microwave and see the food as it cooked, well, then you would say we probably should put a window on the front of that thing. And if we put a nice window on the front, then that'll allow people to look through and to see their food. But if you put a window on the front, you'll let the visible light rays move through both ways, but you'll also let the microwaves move through both ways. And people said, whoa, 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 I want the little water molecules in my food spinning. I don't want the water molecules inside of me spinning. And people thought that that was generally why. So here's what they did is they took a sheet of metal and they poked some holes in it. Those holes are small enough that wavelengths that are nice and small, like the wavelengths from visible light, those wavelengths can sneak on through the cracks. But waves that have slightly bigger wavelengths, like those from microwaves, those wavelengths are too big to fit through the little opening. And so the microwaves can't fit out through the little holes in the little grate. But the visible light waves can. So you can see your food without letting any microwaves go in and out of the microwave. That's the idea of a microwave. Now, below microwaves, there are also other frequencies of light that are even lower, and we call this range of frequencies here radio waves. Now students say, wait a second, Miss Wilson, when you say radio waves, do you literally mean like the waves from the radio that like get sent to my car so that when I listen to the radio station, like those are the waves that are coming to me? Yes, that's exactly what I mean. Radio waves have a frequency lower than that of microwaves. They have a nice long wavelength. Now, this is one of those like lessons that's very quickly going to become outdated because pretty soon no one's going to remember what a radio is anymore. But for today, I'm hoping that you still remember, hey, did you know that there are two different types of radio stations? There are AM radio stations and there are FM radio stations. If you know anything about the radio, you know that the FM radio stations are our local radio stations, like 97.3 KBCO. That's an FM radio station, and it only really services places around Denver. But then there are other radio stations, like on AM frequencies, and those radio stations can travel much broader distances. They go like all the way across the country. Well, that's because AM radio waves are a slightly lower frequency. They have a slightly longer wavelength. They can have a wavelength of up to like 104 meters. That's like a whole football field long of a wave. And so those radio waves can travel much greater distances without much disruption. The FM radio waves are a little bit shorter, and so they are mostly used to service locally. Now, if you ever looked at a radio before and you decided to turn your dial to 97.3 KBCO, what actually is 97.3? Like, what is that number about? It's telling you the frequency of that radio station. That radio station is transmitting radio waves at 97.3 megahertz. 97.3 megahertz. And so that is literally the frequency that you are listening to. And that, ladies and gents, is the electromagnetic spectrum. All of the different types of light, from radio waves all the way up to gamma rays. Now, there's one last thing that you need to know for today, and that is a little bit about calculating wavelength and frequency when it comes to different types of light on the electromagnetic spectrum. Here's something that you already know. You already know that V equals lambda. That the speed of a wave equals the frequency of that wave times the wavelength of that wave. Well, here's a new equation for you. If the speed of light is always equal to c, then we say that c is also equal to lambda. C equals frequency times wavelength. So if you know the speed of light, and you know the frequency of a light, you can calculate its wavelength. Or if you know the wavelength of light, you can calculate its frequency. Let's go ahead and try an example. Say that I was wondering, what is the frequency of light that has a wavelength of 600 nanometers? Well, here's what you would do. you would say, well, I know my original equation, C equals F times lambda. Then we would rearrange to solve for what we're looking for. We're looking for the frequency. So we can say that the frequency is equal to the speed of light, c, divided by the wavelength, lambda. Then plug in numbers and solve for our final answer. You know that c is equal to 299792458 meters per second. 2997924, almost there. 5, you got it, 8 meters per second, lovely. Divided by our wavelength here is 600 nanometers. You do have to do a little bit of a unit conversion, and you do have to know what nano means. That's going to be 600 times 10 to the, do you know it? -9th meters. Plug that into your calculator and you'll find that you get something like 5 times, I'm just using 1 sig fig here, 10 to the 14th hertz. And that is a little bit of a yellowish green kind of color of light, is that particular frequency. Well, today you learned a lot about what electromagnetic waves are, and you learned 3 fun facts about them. Then we talked about polarization, how polarization works, what unpolarized light is, what polarized light is, how polarization filters work, how snow or horizontal surfaces can polarize light. Finally, we talked about the electromagnetic spectrum. We talked about all of the different types of all the frequencies of light, and then you learned how to do a calculation for the frequency of a light if you were given the wavelength of that light. And that's all for today, folks. I hope you have a wonderful, wonderful rest of your day. Bye, good people. Wow, and I totally forget how to stop this now. Yeah. Oh, right here. Wow, that was embarrassing. Okay, bye, good people, for reals.